Alrighty, good morning, fellas. I think we're still waiting on some folks. I did just post that link. My earlier Calc 1 class ran a little bit later because it was a review day and they wanted to ask lots of questions. But today is also your guys' review day. So this is our last class meeting before exam two. Exam two, and then there's going to be the day we come back from spring break. So today is your guys' chance to ask any questions from the homework that you would like to look at, kind of in preparation for the test. So if you could, please, in the chat, tell me what problems you want to see. If you want to see homework 6, problem 5, just type homework 6, problem 5. I'm going to refill my coffee. And as soon as I get back from that, I'm going to begin solving those problems. All right. So yep, so you reviewed it. There will always be some true false, and there will always be some multiple choice. We can go over the sections that will be on the test. It's everything we've covered since exam 1. If you want to practice the true false questions, the best place to find those, go to the chapter review. So right, here's chapter 4. At the very end of chapter 4, there's a review. These concept check questions are very good. And then there are a bunch of good true false questions. And these true false questions are quite similar to the true false questions that I put on the test. They're worded and concept focused in exactly the same way. So those would be a good thing for you guys to practice if you're nervous about the true false questions. The chapter 3 review is also worth looking at, right? Because there's a meaningful amount of chapter 3 material on our test as well. We want to go over the sections that are going to be on the test. So the sections on the test. MAC 2311. So H1 lecture. And the date today is the 4th of the 5th. Review for exam 1. Review for exam 2. Sections on exam 2 are, I'll this over here. So we left off last time at the chain rule. So we're going to pick up at 3.5. Implicit differentiation. And then 3.6. Derivatives of logs. And also in this is logarithmic differentiation. 3.9 was the next one we covered, which is related rates. And then we jump to 4.1, which is axis. Then we have 4.3. The derivative x graph. And then 4.4, 4.5, 4.4, which is L'Hopital's rule. Indeterminate forms. 4.5, which is curve sketching. Four point 7, which is applied optimization. So these are all the sections that are going to be covered on exam 2. Of course, the exam 1 sections are relevant here. It's not like you can forget the power rule or forget the product rule. We use those all the damn time. But these are the explicit sections that we've learned since exam 1. So these are the sections that will be emphasized. Oh, you guys can't see, can you? Well, all right, I'll hold here for a second. I'm going to review the chat, see what sort of things we can do and in what sort of order. Yeah, so I'm actually uploading right now. I started uploading this morning the lectures from earlier in the week. I'll be double checking this afternoon to make sure everything is up to date. So you'll have access to all the lectures. So I see Kevin wants to see some problems having to do with indeterminate forms. Certainly there will be true-false questions, and you can study for those by looking at the chapter reviews. So let me do this really quickly. If you go to like the chapter 3 review, and you scroll down here, you see the true-false quiz. These are really good true-false questions. They're very similar to the true-false questions I asked. In fact, I bet if you look through these, you will see some that are the same. And then similarly, you can go to chapter 4 review. These concept check questions are very, very good and worth looking at. And then again, the true-false questions, super similar to the ones I asked. These might even be a little bit harder than the ones I asked on the test, but if you practice these, then you'll be in good shape for my true-false. Okay. So indeterminate forms problems. Yeah, actually, there's one particular indeterminate form problem that I want to look at. It's a challenging one. It's on your homework. So let's begin with, actually, yeah, what the fuck, let's do it. When x to infinity, 1 plus a over x raised to the power of bx. So if you just try to plug in at a glance, this looks like 1 plus 0 raised to the infinity, right? A over x, as x goes to infinity, that's a over infinity, which is 0. And b times x, as x goes to infinity, for any constant b, that's still going to go to infinity. So this looks like 1 to the infinity, which is an indeterminate power. The way we handle indeterminate powers is by using the natural log to turn the power into a product, and then using some clever algebra to turn the product into a quotient. So I would begin here by saying let f of x be the function I'm trying to take the limit of, 1 plus a over x raised to the bx. So the ln of f of x is equal to the ln of 1 plus a over x raised to the bx, which is bx times the ln of 1 plus a over x, which means the limit as x goes to infinity of the natural log of f of x is equal to the limit as x goes to infinity of bx times the natural log of 1 plus a over x. And now if we look at this guy as x goes to infinity, the bx piece here is still going to infinity. And the natural log of a over x is going to the natural log of 1. But that's infinity times 0, which is an indeterminate product. And that's what we said would happen, right? We take the log, and instead of getting an indeterminate power, now I get an indeterminate product. So we kind of reset and ask, okay, how do I deal with indeterminate products? Things like infinity times 0. Does anybody remember the rule or the strategy that we use to attack these sort of things? Very good. Yeah, exactly. We're going to make it a ratio. Katie and Kevin are both perfectly on the mark there. We're going to make it a ratio. And the way we do that is by shoving one of these terms downstairs as its reciprocal. So I've got a choice. I could rewrite this as bx divided by 1 over the natural log of 1 plus a over x, or the natural log of 1 plus a over x divided by 1 over bx. And I'm thinking ahead to L'Hopital's rule. Easy choice here. I would way rather differentiate 1 over bx than 1 over the natural log of 1 plus a over x. So I'm going to shove the bx term downstairs. So this becomes lim x to infinity, natural log of 1 plus a over x, all divided by 1 over bx. Algebra-wise, this is totally kosher, right? This simplifies to this. But calculus-wise, now, as you send x to infinity, the top is still going to the natural log of 1. The bottom is going to 1 over infinity. That's 0. So this is 0 over 0, which is now an indeterminate ratio, which is good news, because that means I can L'Hopital. So I L'Hopital. Johann Bernoulli says, if you want to, and you have a 0 over 0 limit, if you want to, you can take the derivative of the top and the derivative of the bottom and try again. I certainly do want to. So what is the derivative of the top? Remember that the natural log of some stuff all primed is equal to 1 over that stuff times the derivative of that stuff. So the derivative of the natural log of 1 plus a over x is going to be 1 over 1 plus a over x times the derivative of 1 plus a over x. I'll just write that in the prime notation. That's my upstairs. And downstairs, I'll have the derivative of 1 over bx. Which I can write in the prime notation also. A over x and 1 over bx are both constants times 1 over x. So those derivatives can be calculated using the power rule. This is 1 over 1 plus a over x times the derivative of 1 is 0. The derivative of a over x is negative a over x squared. Just think of it as a times 1 over x. 1 over x has derivative negative 1 over x squared. So that constant a comes along for the ride. And similarly, downstairs, think of this as 1 over b times 1 over x. His derivative would be negative 1 over b times x squared. And now we've got some algebra to do. When x to infinity, 1 over 1 plus a over x times negative a over x squared times, I'll bring this term back upstairs as negative bx squared over 1. And we can cancel the x squareds, multiply negative a times negative b, we get lim x to infinity ab divided by 1 plus a over x. But a over x is still going to 0, so as x goes to infinity, this goes to ab over 1 plus 0, which is just ab. What we arrive at is that the natural log of my function goes to ab. And this is when x to infinity, natural log of f of x is equal to ab. We know that when x to infinity f of x itself would be e to the ab. And that's our answer. So this is a really good problem. This is a, if you can kind of feel your way through this problem on your own, it's a good measure of how comfy you are with L'Hopital's rule and all the sort of things that can happen with indeterminate products and powers and ratios. All the work here is a little bit challenging. I won't pretend like that's not the case. Each one of these steps is a little bit harder than average. So take a second, look at your work, look at the work I have here, and see if there's anything you'd like to ask about. Any questions on this one? All right, Julio, I did go ahead and mute you there. We're just getting some rustling sounds from your microphone. But if you want to ask something or talk at all, feel free to unmute yourself. All right, the next questions that were requested were from homework 8, problems 12 and 13. So let me pop that open. Here's you guys, homework 8. All right, yeah, these are both indeterminate power things. So we can fiddle our way through this. I want to take the limit as x goes to 0 from the right of the tangent of 3x to the x. Just raised to the x, or is it 1 over x? Just x. Okay. So in the same spirit as the last problem, I'm going to start by just plugging in and see what I get, because that kind of tells me what to do. If I just plug in 0, I get the tangent of 0 raised to the 0. What is the tangent of 0? Yeah, my wife's shouting out answers in the background. You guys know this stuff? I don't know if we could hear her. Yeah, it's 0. All right. So this looks like 0 to the 0, which is also an indeterminate power. Just to be clear, I want you guys to make sure you know your indeterminate powers. You should know all your indeterminate forms. The indeterminate powers are 1 to the infinity, 0 to the 0. There's one more. Does anybody know the last one? Scroll in, scroll in, scroll in. Oh, there it is. 0 to the 0, 1 to the infinity, infinity to the 0 is also an indeterminate power. All right. So you see any of those, then we're going to attack the same way. I'm going to call this thing f of x. And say, all right, that means the natural log of f of x is the natural log of tan 3x to the x, which is x times the natural log of tan 3x. And now instead of trying to take the limit of f directly, I will take the limit of the natural log of f. My limit is sending x to 0 from the right, so lim x to 0 plus ln of f of x equals lim x to 0 plus x times the natural log of the tangent of 3x. Now, as x goes to 0 from the right, x itself, of course, is going to 0. What is going on in here? As x goes to 0, tangent of 3x goes to 0. What does the natural log function do as its inside goes to 0? We can write this as a 0 plus if we want, by the way, just to indicate that it's going to 0 in a positive way. Can you guys picture the graph? Forget the natural log for a minute. Can you picture the graph of tangent 3x? It looks like a regular tangent graph, which is kind of like x cubed. Oh, I've got a Desmos window up already. Whoa, weird scales. Okay, hang on. A little better. So here we are close to 0. As x goes to 0 from the right, tangent of 3x is going to 0. And it's going there in a positive way. So this would be like the natural log of 0 plus. What is the natural log of 0 plus? What does the natural log function do as its inside gets closer and closer to 0 from the right? Very good, goes to negative infinity. This is also coming from our knowledge of the graph, right? If I look at y equals ln of x, as the inside goes to 0 from the right, the whole thing is diving down to negative infinity. Here's kind of our larger picture natural log, right? So as the inside goes to 0 from the right, this thing is going down to negative infinity. So this is like 0 times negative infinity, which is an indeterminate product. Oh, sorry. So again, we take an indeterminate power and turn it into an indeterminate product by taking logs. That means I should try to turn this into an indeterminate ratio. And again, I can shove either one of these pieces downstairs as its reciprocal. I would way rather differentiate the reciprocal of x than the reciprocal of the natural log of the tangent of 3x. So I will write this as ln tan 3x divided by 1 over x. Sometimes if you're unlucky, the nicest way to write this doesn't yield the nicest result. So, sometimes you'll have to go back and change that choice, but let's see what we get. As I send x to 0 from the right now, the top is still the ln of tan 3x. That's still going to negative infinity. The bottom is going to positive infinity. 1 over x, as x goes to 0 from the right, goes to positive infinity, again coming from the graph. And this is an indeterminate ratio. So I am now Gucci to L'Hopital this thing. So let's do it. If I apply L'Hopital's rule, that means I'm going to differentiate the top and the bottom and see what happens. Here I will get 1 over the tangent of 3x times the derivative of the tangent of 3x. And downstairs, I will get negative 1 over x squared. And that makes me a little bit nervous because there's no obvious cancellation here, but maybe something nice will happen up here. The derivative of the tangent of 3x, so this is lim x to 0 plus 1 over the tangent of 3x times, this is going to be secant squared of 3x times 3. So it's kind of 2 layers of chain rule here. And then downstairs, I still have negative 1 over x squared. So I should try to clean this up algebra-wise and see what I get. I'm going to just step over here to do some algebra for a minute. 1 over the tangent of 3x is 1 divided by sine 3x over cos 3x, which is cos 3x over sine 3x. Ooh, this is going to be fun. I see what this is. And then I have secant squared of 3x. That's 1 over cos squared 3x. So what do I have all together here? I have lim x to 0 plus 1 over the tangent of 3x is cos 3x over sine 3x times secant squared of 3x is 1 over cos squared 3x, and then I still have that 3. And then I also have this 1 over x squared downstairs. I'll bring that upstairs as negative x squared over 1, just to see what I can do with these pieces. Of course, I can cancel one of these cosines here with the cos squared there. This becomes lim x to 0 plus 1 over sine 3x times 1 over cos 3x times negative 3x squared. All right. This should remind you of one of the problems we looked at back in the day, one of those special trig limits. This term here is not problematic. As x goes to 0, cos 3x goes to 1. So this piece is just going to 1. And I think it's worthwhile at this stage to remark that so we can kind of stop worrying about him. This guy is going to 1. So I'm not worried about him. I can sort of group terms here as lim x to 0 plus, I'll take an x, or I'll take a 3x and put it over top the sine of 3x. And then I've still got a negative x here. There's more than one way to skin this cat. Maybe what I should do instead of that, let me do it like this. This will look more reasonable to you guys. Right, so I've got this. All right, this piece goes to 1. So I just multiplied this and this. So I've got negative 3x squared over the sine of 3x. And if you plug in 0 for that, you're going to get 0 over 0, which is another indeterminate ratio. So I can apply L'Hopital's rule again. There's another way to do this, but I think as you're solving L'Hopital rule problems, this is what you're going to want to do. This is what's going to feel most natural. So let's do it like this. So we've done some algebra and one run of L'Hopital's rule. I'm going to do one more run of L'Hopital's rule here. And I'll get lim x to 0 plus, this will become negative 6x. And downstairs here, I'll have cos 3x times 3. And now if I send x to 0, I get negative 6 times 0 over cos of 0 times 3, which is 0 over 1 times 3, which is 0. So we've shown that the limit as x goes to 0 plus of the natural log of f of x is equal to 0, which means that the limit as x goes to 0 plus of f of x itself is e to the 0, which is 1. So that's your answer here, 1. It required the natural log thing and then 2 runs of L'Hopital's rule. You could have escaped the second run of L'Hopital's rule at this stage by grouping terms very carefully and applying the sine x over x limit that we learned. But I think this is probably easier, faster, clearer, especially given that you'll be practicing more L'Hopital's rule right now. Questions on this? So what was the other one we wanted to see here? So it was 12 and 13, right? This one you can attack the same sort of way. So we've done this one and we've done this one together. I would like to leave at least one of these for you guys to approach on your own. So I'd say go ahead and try the same thing here. This base is going to 1. This power is going to infinity. So this is a 1 to the infinity indeterminate form. Take natural logs and attack it the same sort of way we did these first two. Homework 8, problem 30. Let's do it. Yeah, nice. All right, e to the sine x. We want to sketch e to the sine x following the guidelines from curve sketching. So those guidelines, remember, they're quite complicated. I'm going to do my best to do this quickly because this could take the whole class period if we weren't careful. So we're going to say sketch y equals e to the sine x The domain. Well, the domain for sine x is all real numbers. We know that. And so there are no red flags here. E to the stuff doesn't care what sort of stuff you feed it. So the domain is all real numbers. Intercepts. E to the sine x is definitely never equal to 0 because e to some stuff, no matter what the stuff is never equal to 0. Exponentials are never 0. Focus, you fuck. But the y-intercept, e to the sine of 0 is e to the 0 is 1. So there's no x-intercepts, and the y-intercept is the point 0, 1. Next up, we would check for what symmetry and asymptotes. So here, f of negative x is e raised to the sine of negative x. Sine is an odd function, so I can say that's e to the negative sine of x. But this is not equal to f of x nor negative f of x. So I don't expect any symmetry. I have no reason to expect any particular symmetry here. So this is neither even nor odd. However, sine x is periodic with period 2 pi. And f of x plus 2 pi is e raised to the sine of x plus 2 pi. And because sine is periodic with period 2 pi, sine of x plus 2 pi is the same as sine of x. So this is e to the sine of x, which is f of x. So f of x plus 2 pi is equal to f of x. So f is periodic. With period 2 pi. So no even or oddness, but we are periodic and our period is 2 pi. So once I know what this function looks like from say 0 to 2 pi, I can just copy paste, copy paste, copy paste. Now the good stuff. Mins, maxes, and increasing, decreasing. Y primed is e to the sine x times the derivative of sine x, which is cos x. Or you can write it as cos x times e to the sine x if you want. So this is going to be equal to 0 if either of these factors is equal to 0. If e to the sine x is equal to 0, and this happens never, we already said that, e to some stuff can never be 0, or if cos x is equal to 0, and this happens all the time. Cos x is equal to 0 at pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. Cos x is equal to 0 if x is equal to any odd multiple of pi over 2, i.e. x equals plus minus pi over 2, plus minus 3 pi over 2, plus minus 5 pi over 2, and so on. So odd multiples of pi over 2 are the critical numbers for this function. I'll just plot a few of them here. Careful him. I'll graph this thing from 0 to 2 pi, right? Because we said we're periodic with period 2 pi, so I'll put pi over 2 here. 3 pi over 2 here. I'll ignore all the rest for now. all right, Hammy. I can test x equals 0 to the left of pi over 2. If you plug 0 into y prime, you get cosine of 0 times e raised to the sine of 0. The cosine of 0 is 1. The sine of 0 is 0. So this is 1 times e to the 0. The y prime of 0 is 1 times e to the 0, which is 1. In particular, it's positive, so we're increasing. And then between pi over 2 and 3 pi over 2, I could test x equals pi. Y prime of pi, well, that's the cos of pi times e to the sine of pi. Cos of pi is -1. Sine of pi is 0 again, so this is e to the 0. So this is -1 times 1, which is -1. So in particular, we're negative here. And then to the right of 3 pi over 2, I could test 2 pi. And so y prime at 2 pi is the cos of 2 pi times e to the sine of 2 pi. The sine of 2 pi is again 0, cos of 2 pi is 1, so this is 1, which is positive. So I have a local max here, and I have a local min here. I should figure out the y values of those things while I'm here. So when x is pi over 2, that's our max, as y value. I plug this back into the original. This is going to be e raised to the sine of pi over 2. The sine of pi over 2 is 1. So this is e. So this guy is at pi over 2 comma e. And my min at x equals 3 pi over 2 has y value e raised to the sine of 3 pi over 2, which is e to the -1, or 1 over e. So this is 3 pi over 2 comma 1 over e. So those are our maxes and mins, at least from 0 to 2 pi. Right? But we know the function is periodic with period 2 pi. So once I've sketched it from 0 to 2 pi, I can just copy paste, copy paste, copy paste. We're almost done. The last things we need to do are find concavity and inflection points. So for that, we need y double primed. Y double primed is the derivative of y prime. That's d dx of cos x times e to the sine x, which is a product rule thing. So I'll differentiate cos x. That gives me negative sine x, leave e to the sine x alone. And then I add that to what I get when I leave cos x alone and differentiate e to the sine x. That's going to give me e to the sine x times cos x. So this is, I can factor out e to the sine x. And then what's left here is going to be cos squared x minus sine x. Let's see, now this is going to get a little bit hairy. I think what's going to be the easiest way to do this? I'm going to rewrite cos squared x as 1 minus sine squared, because remember what I need to do? I need to figure out where y double prime is equal to 0. So let me jump to a separate page here and start working on that. So if I want to find inflection points, make a number line for y double primed, I need to know where y prime prime is equal to 0. That's equivalent to saying 0 is equal to e to the sine x times cos squared x minus sine x. We know that this factor is never 0, so I can ignore him. But this piece I need to continue working with. So this is true if and only if 0 is equal to cos squared x minus sine x. And this is actually a fairly complicated trigonometric equation. The trick is going to be to use the identity sine squared x plus cos squared x equals 1 to rewrite cos squared x as 1 minus sine squared x. You guys remember solving trig equations like these back in your trig class? So this is 1 minus sine squared x minus sine x that I need to set equal to 0. And I can rearrange that as negative sine squared x minus sine x plus 1. And then I would cross my fingers and pray that this factors. I don't think it factors in any obvious fashion though. So my AC method here, -1 times +1 is -1. Two numbers that multiply to -1 and add up to -1. It's going to be a little tricky. It's going to be a little tricky. So what I would do here is I would make the substitution. U equals sine x. Rewrite this as negative u squared minus u plus 1, and then apply the quadratic formula. So this would mean u is equal to negative b, which is 1, plus or minus the square root of b squared minus 4ac. So it's plus or minus the square root of -1 squared, which is 1, minus 4 times -1 times +1. All over 2a, which is going to be -2. So this is 1 plus and minus the square root of 1 minus 4 times -1 times 1. So that is 5 all over -2. So these two values for u, so u is equal to -1/2 plus √5 over 2, or -1/2 minus √5 over 2, which is pretty fucking awful if you think about it. Because we still have to figure out what x is. These are the values for u, which means sine of x would be equal to this. So x, so this would mean, this is a particularly nasty one, equals -1/2 plus the square root of 5 over 2, or sine of x equals -1/2 minus the square root of 5 over 2. And these are not nice numbers. All right, you take the inverse sine of both sides. X equals the sine inverse of -1/2 plus √5 over 2, or x equals the inverse sine of -1/2 minus √5 over 2. These are ugly enough that if I were, I might want to double check and make sure we didn't make a mistake somewhere leading up to this, but I'm pretty sure we're actually good here. So this derivative was definitely correct. This was a straight up chain rule thing. So now when we apply our product rule here, what do we get? I differentiate this, leaving this alone. The derivative of cos x is negative sine x, so that's correct. And then I add that to what I get when I leave this alone. So there's the cos x, and I multiply by the derivative of this, which is e to the sine x times cos x. Multiplying cos x times cos x is cos squared. So this is cos squared x times e to the sine x minus sine x times e to the sine x. I can factor e to the sine x out, and I get cos squared x minus sine. Now, no, this is correct. It's just brutal. This piece is never 0. That's true. This piece would be equal to 0. So we set this equal to 0. Cos squared is definitely 1 minus sine squared. So this is negative sine squared minus sine plus 1, which is this, after we make that substitution. And we solve that using the quadratic formula. And this is correct, right? This will become plus, yeah, so that's root 5. So this is 1 over -2 plus root 5 over -2, which would actually be this one. And then the other one is this. Yeah, this is correct. These are just brutal. All right. So we might use a calculator at this step to estimate these numbers. I can ask for the inverse sign of -1/2 plus square root of 5 over 2. So that's about 0.66. And I can also ask for the inverse sign of -1/2 minus the square root of 5 over 2. Whoop, what's the issue? Oh, yeah, this is bigger than -1. So this actually does not exist. Right? You cannot take the inverse sign of such a number. So this is a DNE. I would not have caught that on my own. Not that thinking for a minute at least. So we just have this one possible inflection point. And our number line for y double primed would be here. I'm just going to call this x1. Right? And it's approximately 0.66. So to the left of it, I could test x equals 0. When x is equal to 0, y double primed, which is this thing up here, would be e to the sine of 0, which is 1. E to the sine of 0, which is e to the 0, which is 1, times cos squared of 0 minus sine of 0. Cos squared of 0 is cos of 0 squared, which is 1 squared. So this is 1 times 1 minus the sine of 0 is 0. So y double primed of 0 is e to the 0 times 1 squared minus 0, which is 1. In particular, it's positive. So it'll be concave up there. And to the right over here, bigger than 0.66 would be like pi over 2 is probably my next easy number to work with. So I test that. Y double primed at pi over 2. I know pi over 2 is actually a little bit bigger than 1, so I'm not worried about this being smaller than 0.66. We could use pi over 4 or pi over 3 even. But this one works. So if I plug pi over 2 into y double primed, I'll have e to the sine of pi over 2. Sine of pi over 2 is 0. No, sorry, the sine of pi over 2 is 1. So this would be e to the 1, or e, times cosine of pi over 2 is 0. So this piece is 0 squared minus 1. So this is e times -1, which is negative. So we're going to be concave up to the left of this number, concave down to the right of this number. Let me put my two number lines here as close to each other as I can. So then the game is going to be to find, let's see, where this guy is in this setup. So let me draw my 0 to 2 pi number line, and this is where I'll put the shape of my function. I'll mark 0 over here and 2 pi over here because I'm periodic with period 2 pi. So I know I just need to figure it out from there to there. All right. Numbers that need to go on here. Pi over 2 is 0.6. So 0.66 related to pi over 2. Pi over 2 is bigger than that. So my inflection point, my IP here, x1, I'll put there. And then I've got pi over 2 and 3 pi over 2. This is very sneaky, but I suspect there's actually another inflection point over here. But we're not finding it with our inverse sine function. So this equation that you had to solve for the y double prime thing, this is really brutal. Solving this trigonometric equation is quite savage. And I think getting all the solutions there, what we would really have to do is take this guy and then think about the symmetries associated with the sine function. There's going to be one solution. Yeah, there's going to be one solution between 0 and pi over 2. And then there is actually going to be another one. It's going to be at, rotate up here to get to that height. And you rotate pi minus that. Yeah, so the other one, x2 here, would actually be pi minus x1. It's a very hard trigonometric equation to solve, but I suspect that there's actually another IP over here. It would be symmetric with this one. So I'm going to leave that off for now. So let's come in here and talk about the shape of f in each of these regions and see what we can get. From 0 to pi over 2, we're increasing. So we know everywhere in here we are increasing, increasing. And then at pi over 2, we switch to decreasing. And then at 3 pi over 2, we switch back to increasing. To the left of x1, we are concave up. So we are increasing concave up here. And then we are increasing concave down here. And then we stay concave down. Again, I suspect that there's another IP over here, but let's see what we can get just out of what we have here. So in theory, we might be concave down and then concave up. That's my guess. So the shape of the graph here would be increasing concave up, increasing concave down, decreasing concave down, and that will get us out to 3 pi over 2. At 3 pi over 2, we switch back to being increasing, so we're increasing, and then I think it's going to be a sort of symmetric thing. So let me see what I have so far. We said our y-intercept is 0, 1. I'll mark x1 here. I'll mark pi over 2 here. I'll mark 3 pi over 2 here. And we'll see if we can get something good from there to there. At pi over 2, we know we have a local max. It's pi over 2 comma e. So if that's 1, e would be like way up here. And I know I have an IP between them, so I should be increasing concave up, increasing concave down, and then decreasing concave down. Yeah, and there's x2 is going to be like right in here. Yeah, sorry, it's not over there. It's over here. There will be another IP here, and then we'll go back to decreasing concave down. Something like this. So this is an especially challenging one, and I don't want to burn too much time. So let me check a few things really quickly. Let me first see if there is a nice set of solutions to that trig equation we had, which was cos squared x minus sine x. Yeah. Brutal, absolutely brutal. Okay, I'm not crazy. Yeah, but we do have quite a few solutions. So there's going to be, here's the IP we found. It's the very first one right here. We just focus from 0 to 2 pi. Yep, and they're the numbers that we thought they would be. That makes me feel better. They're writing them as inverse tangents rather than as inverse sines, but that's fine. Because the inverse sine function has that domain issue that we ran into. So yeah, there's two IPs right in here, and then there's going to be two more out here. This is what we were thinking. So if we wanted to continue plotting this, we have our local min. It's going to be way down here. This is a 3 pi over 2 comma 1 over e. It should actually be smaller than the 1 here. And then we're gonna repeat. We're gonna do the same sort of thing. We're gonna do something like this until we hit our next IP, and then we'll turn around like this. And we'll turn around until we hit our next IP, and then we'll come out like this. And at 2 pi, we'll be back up to 1. So really, we should be coming down a little bit lower here because 1 over e is smaller than 1. And this would be a reasonably good picture of this graph. It's not an easy thing to sketch. I acknowledge that fully. And the real challenge here is figuring out where this thing is equal to 0. That's certainly harder than anything I would give people in a trig class. So I wouldn't expect you guys to be prepared to solve these. I guess I can show you how to do it. Do we want to see exactly how to find all the solutions to this equation? You kind of take this first guy, and then you use the symmetry of the sine function to locate the other ones relative to him. I think if you get the increasing and decreasing stuff right here, you can start to get a pretty good idea for what's going on. Looks like there isn't a serious thirst for that, so I might leave this one here. This is certainly a challenging problem. We can check our work. Let's see what this says here. E to the sin x. Looks about right. Yeah, so we're starting up here at 1. We increase until we get to a local max at pi over 2. Then we decrease until we get to a local min at 3 pi over 2. And then 2 pi would be right here. I don't know. So we did good, actually. Yeah, let me resketch this. We didn't really fuck this up. The next IP is going to be to the right of that. Oh, no, it's not. Yeah, there's two IPs. There's one here and there's one here. Yeah. So we won't have to worry about those. But this is our guy from there to there. So if we focus just on this piece, because 2 pi is like right here. And then you could cut and stitch these. So certainly a very challenging problem. This first IP is the number x1 we found. This is the inverse sine of -1/2 plus the square root of 5 over 2. If you wanted to locate the other IPs, the inverse sine of that number is like, we'll say that the height right here is -1/2 plus root 5 over 2. So this angle here is that inverse sine. This is x1. The other solution would come from the symmetric point over here. This would be x2. And the way I would normally write that is I would say x2 is pi minus x1. Making use of the symmetry there. But certainly that's nasty, right? Nobody wants to write these things down. Pi minus the sine inverse of -1/2 plus the square root of 5 over 2. And I have no idea what that is in degrees or radians. It's just, I mean, it's this, but it's not nice. All right, in the interest of using our time wisely, let me see what else we wanted to look at. Are there other problems we wanted to look at? Do we have time left? A little bit of time left. Yeah, this is indeed a very tough one. And it really all comes down to solving that equation for y double prime equals 0. It's very, very tricky. We have about 9 minutes left. Are there any other problems that you guys would like to look at in those 9 minutes? Did I lose you guys entirely on that one?
There are many different types of problems that they suggested in the chat.
Many different kinds of problems that what? I just couldn't hear the last few words there, Julio.
Oh yeah, like a lot of people suggested like different kinds of problems in the chat.
Oh, did I miss something? Let me see. So, make the ratio, switch the camera, will it be any true false? Homework 8, 14 and 30. Did I not look at those? We can look at 14 and 30. 12 and 13 we looked at. 8:30. I think maybe 14 and homework 8:14 is the only one that's been requested that we haven't done. But I think that was the other indeterminate power problem, right? Yeah, no, so okay, so we did do homework 8, 12 and 13. We did 12 and 14 from homework 8. I don't want to do 13 because that means that I've done all of the indeterminate power problems for you guys. And then homework 8 number 30 was the one we were just working on, right? So yeah, homework 830 is just brutally hard. There's the equation you need to solve for the second derivative stuff there is very difficult. But I think that's everything that you guys have asked for in the chat. We've gone through now. So are there any other things that you guys would like to look at? Let's see. Unless for some reason my chat window isn't refreshing, I'm going to close it and reopen it. Yeah, no. Yeah, we've done everything that was asked for in chat with the exception of the one I don't want to do because it's the only indeterminate power problem that we haven't done together. So I don't want to do number, what was it, 13 for you guys. I want you guys to figure this out because we did this one 12 and we did this one 14 together. All right, if there isn't any other stuff that you guys want to do, I will go ahead and end the class. I'll say this, over spring break, please make sure that you work the study guide problems. Do yourself a favor and spend a little bit of time every day on these. If you spend 30, 40 minutes a day on these, then it won't feel awful. If you wait for the last day of spring break and try to cram it all in there, then it will feel awful. So please take the time to do these problems carefully, or sorry, yours is here. Take the time to do these problems carefully. Spend, yeah, just around an hour a day, maybe even a little bit less. There's only 15 problems here. They're not that bad. And as long as you do that, you will be in good shape. Remember on these curve sketching problems to actually work them out on your own. Don't just guess the graph. That is not solving the problem. You need to go through the process with the number line. But yeah, I don't think you'll find this too bad. So a little bit of time every day. I'll be checking the Discord daily and email daily, and I'll do my best. No, I'll have one office hour over break. But that's the plan. Is there anything you guys want from me before we sign out?
Is it possible to extend some of the homework assignments?
Sure, yeah, I see here since yesterday I've gotten some extension requests. So if you want a homework assignment extended, submit an extension request and I'll go in and clear those out right after class.
Okay, got it. Thank you.
Of course. Anything else, lads and ladies? Alrighty then, I hope you guys have a lovely break. Please remember to do some mathematics from time to time. And if you haven't updated me about your honors project, you need to do that before the end of the day today. You gotta let me know what you're doing. At least send me an email, I mean something, right? So I know about where you are and I can provide you some guidance. Ideally, you would come by my office hour today, but give me some indication of where you are with your honors project, even if it's I haven't started. That way I know where you're at and we can work together to get moving. But that's it. Take care, guys. Have a good day.